Good morning, everyone. Today I'm going to explain to you about geometrical isomerism, the details involved in geometrical isomerism. So I'm taking two models here. This one is 1,2-dichloroethane. You can see that there are two chlorine and they are attached to different carbon atoms, and then you have all of them in single bonds. So what is the beauty of this compound? The single bonds enable the atoms, especially the two carbon atoms, you can rotate at a 360 degree. Okay, so it is possible to rotate and you can get the hydrogen at different positions, and also the chlorine is going into different positions. So a 360 degree complete rotation is possible with 1,2-dichloroethane because of the single bonds existing in the compound. Now let's take another example where we have 1,2-dichloroethene. Now here you see between the two carbon atoms I have a double bond. Okay, so this is carbon-carbon double bond and it is 1,2-dichloroethene. The first compound which I was discussing was 1,2-dichloroethane and it had only single bonds. But in this case, the carbon-carbon double bond is having some restrictions when it comes to the rotation. So let's look at that. Okay, so the carbon-carbon double bond, when you rotate it, you cannot rotate it at a 360 angle. Okay, so there is restrictions in the rotation. You can only rotate to this extent, like that. So what happens is, at this position, you can see that it is at different. The chlorine is on either side and the hydrogen is on either side of the two carbon-carbon double bond. But if I am able to rotate it to this extent, you can see that the hydrogen has gone up and the chlorine has come down. Okay, now the chlorine is on the same side and the hydrogen is on the same side as a result of the rotation. So the restricted rotation is only able to place the substituents at a restricted angle. So as a result, you have two isomers which are possible because of the spatial arrangement of the groups attached to the carbon-carbon double bond. So you can see that when you rotate it partially, the two chlorine on the same side and the two hydrogen are on the same side. So when this happens, we call this as a Cis Isomer or also Z Isomer after the German word Zusammen. Zusammen or Z, another word for it is Cis. That means that the groups attached to the carbon, the same groups lie on the same side of the two carbon-carbon double bond. Now, if they are lying on opposite sides like this, chlorine on the opposite side and hydrogen on the opposite side, then we have the Isomer Trans, also known as Entgegen or Isomer after the German word. Okay, so you have trans isomer when the two groups are lying on either side, and you have the cis isomer when the same groups lie on the same side, like that. So you have isomers developed, also known as geometric isomers, which are only possible in carbon-carbon double bonds or in certain alkenes. And this is due to the restricted rotation about the carbon-carbon double bond. So if you take butene structure, you have 1 butene, 2 butene, and 2 methyl propene. So the 2 butene will exhibit the cis trans isomer. So here you have the structure of 2 butene. So in this case, the 2 hydrogen is on the same side and the 2 methyl groups are on the same side. So this is an example of cis butene because the same groups lie on the same side. And if you take this is also but-2-ene, but you have the 2 methyl groups on either side and the 2 hydrogen on the either side. So since the 2 groups are on opposite sides, we call this as trans butane. So this is possible because of the restricted rotation around the carbon-carbon double bond. So you have the example there of the cis but-2-ene and trans but-2-ene. So I hope this is making clear the concept of geometrical isomerism. Thank you.